go. So, step number one, thank you very much to Jason and to Trios for giving us a space. Hopefully you all, well, I guess you did all find it, because if you didn't find it, you wouldn't be here. Coming to these questions. Like, I want to ask you about, wait a minute, if they're all here, they already answered this question. Anyway, so we've got two good presentations. Tim is going to talk to us about finding bottlenecks in your networks.
No, just
Anything? All right, bottlenecks. Is your stuff slow?
Why slow it?
Why? And then after the mid-break, Brent is going to talk to us about game emulators.
No, just game emulators.
Oh,
Hardware emulation.
hardware emulation. If you have a random piece of hardware you want to simulate in your computer. All right. All right, so tentatively, barring problems, we're going to try to make this our new home if it doesn't work out for anybody. So that also means we have to decide where we want to go for dinner afterwards.
Mm-hmm.
The most important decision of the night.
There's a really good place across the street. It's they do like rice dishes and various things. It's Korean.
There's also an Indian restaurant. They're Pakistani, I think. There's a difference.
Right.
It is very oily, but it is quite good. Very, very, very oily. I saw the lustrous sheen.
And I think there's also a couple of pubs that way. So there's like that for choices. So maybe think about it, and then maybe towards the end we'll all, maybe at the break, we can all contemplate who wants to go. The show of hands, who plans to come for dinner after the meeting?
Well, food.
Who plans to come for food after the meeting? Sorry, I don't want to discriminate.
I'm looking for beer.
So
dinner.
already had dinner.
So it isn't a Japanese donburi. I was wrong. Sorry. Donburi house is across the street.
All right, possibly. All right, so does anybody have any announcements they'd like to do? Calls, right?
So in terms of upcoming meetings, just trying to see what we have for upcoming meetings. We have March, we do not have anything for April, so we are looking for meetings for April and beyond. If you have something that you would like to offer, please offer it. Does anybody have anything they would like to offer? Bob would like to offer something. What would you like to offer?
Do you guys want to see a presentation on a vulnerability scanner?
Do we want to see a presentation on a vulnerability scanner?
Yes.
Oh, yeah. Is there anything that we do?
Is there a free software vulnerability scanner?
I'll try it. Just don't have high expectations for the quality of the presenter, but
Okay, great. So excellent presentation incoming for April on vulnerability scanners. Does anybody else have anything they would like to either see or present?
One thing I was wondering, would anybody like to see the current state of Curve, which is Doug Mullen's 3D graphing project?
Yes.
3D graphics project?
Are you volunteering, Doug, or are you?
I have volunteered to email Doug to see if he basically wants to redo the presentation he did at StarCon for us.
Okay,
If there's
good.
enough people who didn't go to StarCon, I would like to raise it. I will email them.
And Nathan, did you have something?
Sounds cool.
I'm not sure about scheduling, but I've been recently tinkering with IPFS, the Interplanetary File System,
Nice.
which is a very neat piece of software that I would like to do a presentation on.
I should
Okay.
talk to you about this guy who's making one that's specific to video streaming, where the chunks of data are associated to the timestamps, not just
Oh, sounds cool,
the
yeah.
blocks and the block storage.
Okay. Anybody else?
I got a question. Does anybody know of anything that helps visualize your network that's inside of a host, like what your computer is communicating with and various things like that? Yeah.
Hold on.
Can we have something for this?
Maybe that's February's presentation.
Is that today's
I'll cover
presentation?
some of that
Call back
content.
in
All
now.
right. Did you pay him?
No.
Is he a reader?
No, he pays me to promote his events.
Anything else? Or anybody else? Okay, we're always looking, so please always look for things and volunteer other people and volunteer yourselves. The other thing is, looking for a little bit of help in terms of website updates for kwlug.org and possibly wattcamp.com. Is anybody interested in helping with either of those two things? Colin, maybe?
I could do
Anybody
some
else?
Dockery stuff.
Okay, Andrew, maybe? Yeah. Gloria, maybe? Okay. So I will post to the KW Lug discussion list to say what needs to be done. It's mostly the case is, I think that so I found a new source of events for Watt Camp, and also the old sources for Watt Camp are not being updated as frequently as they were, so it'd be great to have 1 or 2 people to help an hour or 2 a week with that. And then also, George has been taking a ton of video, and we haven't been putting it on the website. So those are the main things. So I will post to the mailing list about that.
That's it. Welcome to KW Lug. Thank you, Tim.
So I apologize, I have a little bit of congestion. I'm on the recovery side of it, so I think, yeah.
Look at all that.
It does look nicer. Makes it neat. Makes it look like I'm doing everything. But before we start, I want to give some disclaimers just before the questions start. So this was a relatively fast production of a presentation. In fact, a crazy fast production, considering that I was only in town one of the weekends between when I agreed and when I gave the presentation.
Thank you, Tim.
I usually do about 5 to 10 times more preparation. So the standards that I usually have for the presentations I give, which may not be the best, but are the best I can produce. This is not that. This is going to be quick and dirty. But I think I can do pretty well with quick and dirty. So this is not going to cover everything. I'm not trying to do a survey or go into the deep history or cover any of the nuance. This is just, boxy. Problem, fix it, move on type presentation. These are things I've used. That doesn't mean that they're good. It also doesn't mean that I know how to use them. It's just they solved a problem for me. So turning this screwdriver around and hitting it on the object several times turns out to drive a nail. And this is the same type of thing. So some of these might be, from your opinion, not the best tool for the job or being used appropriately, but they did useful work. And that's my goal here, is to bring out like these things that I've come across that have helped me push past problems. For this presentation, I'm going to be sticking to the terminal. There are a lot of GUI tools. I don't usually use them because I don't know, I'm just lazy. So that is not my cell phone, but so just be aware, like this is all GUI, or this is all terminal based. Okay, so I'm going to break down, so what I'm going to talk about is you've got a bottleneck in the system. And when I say a bottleneck, something's not performing the way you want it to. So that could be that something's changed and become slower. Could be that something was never good enough. And so the question is how do I make it faster? And so just like the classic bottleneck, it doesn't matter how big your bottle is, doesn't matter how big your glass is, it's only the little neck at the bottom of the bottle that controls your performance. This is the same type of thing. You have memory, you have storage, you have CPU, you have networking, but you go upgrade your network adapter and it turns out you're not downloading any faster. Okay, now what? So the point is to figure out what your bottleneck is first, then address your solutions towards that. So I'll break it down into 4 categories I mentioned before: CPU, storage, RAM/swap, and network. So let's start with CPU. So there is a, before I actually show anything with that, I just want to point out I've got 3 tabs here. This left tab is labeled Mac. That's stuff that's running on my Mac. Yeah, sorry about that. And then these 2 right tabs are running in a Vagrant virtual machine. It's Ubuntu 18.04, and that's where I will be doing the bottleneck analysis and so forth. So this left one is stresses, and this is where I'm going to run code that's going to generate load on the system. And then this right tab is analysis, and this is where I'm going to be, quote, the person coming in and looking around, trying to figure out what I did in that other tab. So it's a little complicated, but I think it'll flow pretty nicely. I have put this text here, so it should be pretty obvious where I'm working at any given time. So let's start with a classic problem. Your CPU is overloaded. Well, fortunately, there's a wonderful program called StressNG, which is designed to abuse computers in lots of ways. And they have a little CPU stressor. So I'm going to go C1, that runs a single process that is essentially going to beat the snot out of my processor in this virtual machine. So now we've got a virtual machine that's working really hard. And you're like, it's not doing what I want it to do. Maybe StressNG, rather than being a stress tester, maybe it's the program you want to run fast. It's your web server, your data analytics platform, or something like that. So we're going to go ahead and go to this other terminal, and we're going to understand why is that program not doing as much work as we want it to do. So the first thing I'll do is I'll run top, because duh, that's pretty much what everybody does when they get to a box. Okay, look, my system's busy. It's using 100% CPU, and if you watch this load number, you'll see it starts to go up. Okay, that's cool. So now I've identified this process is StressNG-CPU. That's stressing my CPU. We've all done this before, but there's more to understand about this. So I want to draw our focus to this line right here. And what this line does is it says, okay, your CPU was busy, but what was it doing? Like, what was the CPU busy doing? And this line helps give us insight. So the first thing you're going to notice is, and I'm going to round up, that we've got this 50% number here, not 100%. And that's because this is a dual core machine. So as a result, a process running 100% is only consuming 50% of the processor resources. So that's one thing to let us know. That's one bit of information. The next thing is if we go through these columns, we see that this US column, that's short for user. So that's just like a program that's running. That's what a user space program is. So it's saying the CPU was busy about half the time dealing with programs running on this machine, keeping them running. Okay? So the next column has this tiny number, and it's SY. That stands for system. So programs might want to have some work done on their behalf by the operating system. A program can't talk to the network directly or interact with the file system or do certain operations on its own. So it goes ahead and it says, hey, system, go do some work for me. And the system does work and then calls the program back and says, hey, got your results for you. So in this case, yes, the program is consuming CPU, but the time that's actually running, it's actually running in kernel space. It's the operating system doing the work part of the time. And so this just allows us to know that the operating system is the busy part. If you're writing code, if you're a programmer and you want to make your code faster, and you see that your user space number is low, but your system space number is high, it doesn't matter how much you optimize that loop, how tight you get it, how awesome your code is. It's the operating system's the slow part. Look at how you're asking, what you're asking the operating system to do, and figure out how you can make that faster. So that's one way of directing your attention when you're addressing a bottleneck. Now these next items are vague interests. NI is nice. What that means is, you've ever used a program which says, I'm not going to get in the way. I'm a backup program, and I'm only going to run when you're not busy doing other things. Nice is the indication. It says, hey, by the way, the processes that we're running this percent of the time were processes that were being nice, that were being generous. That means your system was underutilized and some backlog is catching up. ID, that stands for idle. So if this number is 100%, you're busy, your system's doing nothing. If it's 0%, you're busy, your system is 100% busy, has no spare CPU time. And then this one I actually think is pretty important to analyze. WA, that stands for IO wait. I look at this one a lot. So if you're going ahead and say downloading a huge file from the internet and decompressing it through a compression engine and writing to your disk, what's the slow part? Is it the network connection? You maxing that up? Is it the CPU? You maxing that up? Is it the disk? Are you maxing that up? You don't know, but this number can help you identify that. And if it stays in the single digits, 1 to 5%, yeah, that's probably okay. But if that number starts climbing, what that means is that your computer is actually interacting with the disk or with the storage system so much that the code is actually stopping and waiting for the disk to catch up with it. It's writing the bytes, and the disk actually pushes back and says, nope, you can't write anymore for a little while. I'm busy, dealing with the past request. So when you're doing backups and restores, this number will climb up. But if you're like in a normal day-to-day operation where you're saving a file, you're serving files for a web server or something, if this number is getting up, that means you're falling behind. Your storage is too slow. This stands for hardware interrupts. Not going to get into that. Software interrupts. Not going to get into that. Yes, George?
If you have too many access to the disk, it is buffering everything, or if you just flood it with requests.
So there's something called blocking I/O. So you're saying, hey OS, write this block to write this space, like this data to a disk. The OS will actually pause you. Time will stop. Your code isn't running. In the kernel, it's running, but the kernel says, well, you've asked me to write this, but actually I'm not going to write it because the disk is still, holding me back. It's saying I'm not ready to receive another request. So there is a buffer in the middle, but it's not like huge spooling buffer. The code actually stops during this time. So does that make sense?
Kind of. Maybe my question relates to the network traffic or something. Yeah, if you have too many requests, if you have like a flood of input-output requests, and the buffer is full, so what it's doing is discarding the following requests, or.
So that's a network connection, and that's not storage. So you can't prevent network packets from being sent to you, so they just get dropped. But we're talking about disks, spinning.
But the network request might require a write to the disk.
But I'm not analyzing network requests right now.
Okay.
I'm analyzing disk request and disk performance. So whatever is causing the disk to be busy, not actually particularly important. Is the disk too busy or not?
If your program blocks on disk and it stops fetching packets from queue, then it's going to overflow and start dropping packets. Is that what you mean?
Yeah.
Yeah. But I'm being very agnostic. I don't care what's generating the load on the disk. It's just if that number climbs, that means the disk is starting to fall behind. The storage media, whatever you're using, is starting to fall behind the performance that the other parts of the system could request. So it's becoming the slow part.
But the requests to the disk are buffered, yeah? So the request to the disk could come from the network or from the operating system.
There isn't a difference. The requests are coming from some software system on the computer. And it's going out to a physical storage system. It doesn't matter where they're coming from. A network connection is coming in and going to something, somewhere, some software system that is causing a disk request. But yes, there's going to be an intern buffer in some cases, though not all cases. Storage is fiendishly complicated, and you have transparent caches and lots of other things. But it boils down to, if that number gets higher, your storage is slow. Your storage is not keeping up with the workload. And that's all we need to know here from that number. So in this case, though, we're looking at it, storage is not our limiting factor. User space is our limiting factor, right? This is spiking, this is sitting at 0. We're not using the storage at all, so upgrading to an SSD wouldn't solve this problem. It wouldn't make this any faster. And then we have these hardware interrupts, software interrupts, and this last one, ST, is interesting. So this is a virtual machine, and on virtual machines, you'll have this other column called ST. That stands for steal. And what that is an analysis of how much time the CPU wasn't actually available to the operating system. And what do I mean by that? If you have a virtual server, you have a server with virtual machines on it, that means you have several virtual machines running on that box, and you have a hypervisor that's kind of moving things around, keeping everybody satisfied and happy. But you can get into a state which is called overcommitted. You have more workload on that machine than the hardware is capable of doing. And so what the hypervisor does is it cuts a little slice off of everything on the box. It says, your minute is 40 seconds long, and your minute is 40 seconds long, and your minute is 40 seconds long, and it gets an extra minute back per minute. And so this is how kind of these workloads get densified and put in one place. But as it does this, what Steal does is it says, hey, your program is slow, not because the processor is slow, but because you're not actually getting a full minute out of the processor. You're getting a fraction of the time. And so if your steal is at 50%, it means that your program would be running twice as fast, possibly, if it was CPU bound, as it is running, but the hypervisor has stolen the time away. And so this gives you a lot of ideas. Yeah?
Does steal start going up if your VM is idle and being crowded out, or only if you start trying to use that CPU zone?
Good question. I can't say that I know the answer. I suspect that it would be only non-idle time, but I could be wrong. I have no idea, actually. Yeah, I haven't looked into that. But moving on, so we're still sitting here in top, and I want to show you one other trick.
With multiple VMs, you should be able to manipulate the state value, right?
Yeah, you can tune
you can
VMs,
test it.
but
Now we know.
this is just discovering what's going on. So your virtual machine is the problem. Your disk is the problem. Your processor is the problem. That's all we want. We just want to identify where's the bottleneck. The solution, that's a different stage. That's not something I'll be spending a lot of time on. So one other thing I want to show you, which is if you're in top, if you hit the number 1, the digit 1, you'll see the view changes. And so by default, it summarizes all the CPUs. But in this view, you see these stats for every individual chip separated. If you have a lot of chips, this gets very tall. Some people have shown off that way. But if you only have 2 chips, it's pretty easy to read. So now we're looking at this. We understand what all these things mean. And we're looking at it, and what we see is that one processor is 100% busy, and the other one is dead. It's doing nothing. So what have we learned here? We're not waiting on our hard drive. We're not dealing with steal. We're not dealing with the problem like that. And our program is using 100% of our processor. So that probably means our program is what's called single-threaded. It's only able to take advantage of the resources from one processor at a time. So what does that mean when you're trying to deal with this bottleneck? Don't add extra processors to the system. It's not going to go faster. It won't help. Don't add RAM. That's not going to help. Don't prioritize the virtual machine. Give it, make it a higher priority one. Get less steal. That's not going to help. You just need a faster chip. That's all you need. Now, if you want to get around this, if you have a partitional workload, you could run 2 copies of the program and maximize both CPUs at the same time. And so I'll go do that. I'll go ahead and run 2 CPU hogs. And now we see, okay, now we're using the whole machine. So at this point, adding processors, that might speed things up. We don't know. We know that our workload can go across multiple chips, but if you add that 3rd processor and you see it sitting at 0, you know, okay, it's the speed of the processor. It can't spread across and use multiple processors. That won't help. So let's go ahead and run a slightly different CPU stressor. I'm going to run something called get. And when we go back over here and we look at this view, we're going to get a very different view. So I've run something. Remember, this thing is still at 100%, just like before. But up here, this line's very different. Now we have this situation where the user space is not being used that much. It's the kernel that's doing most of the work. And so if you're a developer, you know, okay, look at my system calls, see what I'm doing, because that's the thing that's slowing me down here. Okay, so that's kind of a deep look into top. So let's look at HTOP in this case. HTOP is super popular. People really love it. It has a lot of features. I've used it a little bit, but I don't use it very often. And the reason why is because it's pretty, but it doesn't tell me anything. I could spend a lot of time getting it to tell me more, but it's not installed by default, and it's not telling me all that much. But it is a popular one, so it's definitely worth using. Just realize you're losing some information. You can't debug as strongly. So the one thing I can get from HTOP, I'm single-threaded here, right? It's really clear. I'm not using 2 CPUs, but I can't really tell the nature of that single threading, where that's cropping up. So HTOP is another very popular tool. Highly recommended. It's very easy to use, but I don't use it that often. And my favorite, though, in the realm of tools, is also kind of the ugliest. I guess only the ugly tools could make it to favorite, because otherwise you wouldn't use them. And it is called VMstat. And the thing I like about VMstat is you're on a little terminal, you're on a tiny little box, you have a bunch of screens on the window, and you just want to get a snapshot. Like, if I push this button, does the system get busy? VMstat's perfect for that sort of thing. You don't have a lot of detail. You don't have a lot of screen space being used, but you have a lot of detail. You can see what's going on with the memory of the machine, how much swap and RAM is being used, how active the swap space is. This is huge, and I'll get into this a little later. How active the disk or the I/O subsystem is, how active the context switches are and interrupts, and then this last column, you can see user space, system, idle, wait, and steal. And you get those really nice critical numbers that help you understand, hey, what is the nature of the workload that's consuming the CPU. So just a really great utility, gives you a lot of answers about a lot of things all at once. And I'll be coming back to this a lot. So now we've looked at analyzing processor bottlenecks and thought of a few ways that they're nuanced. There's details to them. Adding extra cores, will that help? Making it faster, will that help? Do I need to actually change the code? Will that help? So you get some more nuance from these tools. So now the next thing is, let's look at storage. I talked a little bit about being storage bound, but let's analyze storage problems. So again, I'm going to run my favorite program, StressNG. I'm going to run their disk, the disk log. So we've got a few programs that we can look at storage with. The first thing is actually, I'm just going to look at top. And because we're hitting the storage pretty hard, you can see here this number is going up. It says I'm storage limited. And this is very significant. It means a third of the time nothing's running because it's busy waiting for the disk. 45% of the time. That's not very good. So this is a case where you might want to see if you can reduce your load on the storage or speed up the storage you've got. But there's a couple of other tools you can analyze your storage with. I have to do this as root. And one of them is a program called IOtop. It's just like top. It sorts the top items that are consuming resources, but this one is focused on disks. And so you can see each process on your machine and what disk activity it's generating. So you can see that the StressNG thing is reading the snot out of the system. It's reading, writing, reading, writing, reading, writing. And so that, if you're finding yourself disk bound, you see your disk weight numbers go up. What's using the disk? Maybe you've got a system with lots of things running on it. You need to identify the thing that's churning. Then this can help you identify that. It works pretty much just like top. So it's called IOtop. And it's very nice, but it's not always installed by default. So, I don't use it as often as some other programs. There's also another one called IOstat, and I like this one because it's kind of a version of VMstat, but for disks. So what this does is it says, hey, look at all the disks. I have 1, 2, oh yeah, it doesn't like it when I click on things here. So give me a second. So I have, the 3 disks. One of these, ignore it. I have this SDB and SDA. So I can see, for example, getting a SSD for SDB, not going to speed things up. Won't help. Let's see. Can I clear it? Actually, I'll just leave it like that.
Can you throw a -X in there?
We just put IOstat 1. One reading.
-1 or?
Just 1. IOstat 1.
No, that updates once a second.
Oh, well, one space 1. It's like star, right? So 1 reading, 1 second.
Oh, 1 space 1.
1 space. There.
Yeah. Okay. Thank you. So this gives you some CPU numbers to give you a sense for like what's going on, and then it shows you which disk is busy because you might have multiple disks. So which is the one that's slowing you down? Oh crap! It's doing all that stuff on the little thumb drive. It should be on the internal SSD. That might be what this helps you understand. And it gives you some actual numbers of like what it's doing. And some of these numbers are useful. So, duh. But knowing how much it's reading and writing, if you get a sense for your hardware, you might know what its maximal capacity is. But this one, the TPS number, it stands for transactions per second. And this isn't a perfect analogy, but it boils down to if you're dealing with spinning media, so a hard drive, not an SSD, there are physical parts moving around in there. And the physicists have some limits on these types of things. In other words, it's only so fast that these heads can move around before they start tearing themselves apart or losing their accuracy. And so the number here, it's about 100 to 120, and 150 maybe. Somewhere under 150, definitely. If you see anything over 100 here, and you've got spinning rust, you've reached the limit pretty much. You're done. You're not going to get any more performance in the form of transactions. Now, if you make your request bigger, maybe you'll get more throughput and more bandwidth moving around, but you can't have the head move around any more than that. You've hit a physical limitation. So that's a good thing if you're working on a server or a box, you see that number sitting at 115, 130 or something. Don't squeeze that disk any harder. You're done. Now, if you're dealing with a RAID or something like that, those numbers are a little more fuzzy. I won't give you any answers there. Also, if you're dealing with an SSD, this is less than 1 trillion. You're probably fine. No, it's not that fast, but these numbers will get a lot bigger. It's probably not the transactions per second that's holding you back. That gives you some more information.
The -X switch might be useful. So you might need the other end of the screen to get to the fun part.
The utilization?
Yeah, I'll actually give you utilization.
Of how much of the disk activity you're utilizing?
I'm not sure how it calculates that, but
that's cool.
It also gives you the details of block sizes hitting.
Yeah, how big and I think some of the queues.
Yes.
Yep, very cool. So -X, but I need to move on. Thank you. So there's VMstat. So VMstat, I love VMstat because it has a disk check, except it uses stupid units, so I always give it unit M. And so this essentially, if you do VMstat-N1, you'll see that you can have statistics printed out. And so here, let me, I'll just do there, one go. And so this shows you kind of how many reads, how many writes, or total reads, total writes, and current activity. So this can give you a sense, again, what disks are busy and what are they up to.
Is this total reads since boot, or?
Yeah, the initial numbers from VMstat are usually bad, by the way. Always run 2 cycles of VMstat data, because the first number is kind of cumulative stuff since they're counters. And so it says, hey, the counter was blank, 0 it out. Okay, now the counter is blank. Is whatever. And so that first number has kind of got some unknown state in it. That second number will actually reflect the 1 second or the 5 seconds or the 10 seconds or whatever it is, the interval that you've set it to. So VMstat-D gives you disk information. Again, this doesn't tell you the program that's giving you trouble. It can tell you that your system's having disk issues. So another one that I'd like to point out is Peavy and DD. So these are dirty tricks, but they work. So actually, yeah, I'll just type it by hand. So DD stands for disk dump. And you can do things like, say, read dev0 for all the data, and it'll get an infinite amount of zeros from dev0. And for out file, I am going to write it to a file called 1 gig. I'm going to set a block size equal to 1024 plus 1, 2, 3 zeros, and I'm going to do a count of 1,000. So I'm going to try to write roughly a 1 gigabyte file in 1,000 chunks. I have an SSD, by the way. So what have we done? So this is not random reads and writes. This will not tell you how fast your database is. But it kind of gives you a sense of, is this fast or slow? Like, what's the scale? What's the t-shirt size on this thing? And so in this case, it says, hey, I wrote 601 megabytes per second. So I call that fast. And so this just gives you a shape of your storage, and it can be helpful. You want a quick disk benchmark. Awesome for that if you have a gigabyte of space to give for it.
Can you put a sync at the end of that?
Sync?
Semicolon sync?
Flag, semicolon sync?
Yeah, just...
It's fast.
It really is.
It's really fast, and this isn't a VM. You should see outside.
Sometimes you get like 5 gigabytes per second.
Oh yeah, no.
An old hard drive.
Yeah, because you're sitting in cache, but a gigabyte is going to blow away all the caches, especially if you only have a gig of RAM. But okay, so this is one thing. Another thing is Peavy. So you don't want to know kind of how busy your disk is. What you want to know is like, I've got things moving. I've got data moving around on my system. I'm taking, say, a database backup, and I am decompressing it and running it into the database restore command. How long is this going to take? It's a big backup. I don't know. Like, is it going to be an hour? Is it going to be 3 weeks? Don't know. Well, Peavy can help you. So Peavy stands for pipe view. And what it is it's an accounting program. Data comes in the left side, it does some math with it, and it sends the same data out the right side and shows you kind of how big it was, how fast it came. So let's look at how fast I can read this file from disk. So I'm going to do cat 1g pipe Peavy dev null. So in other words, I'm going to read the entire file and throw it out. And so you can see I'm reading the file at about 50 megs a second. And so if I know it's about a gig, then, it was 7 seconds or something when it got to 333. So it'll take about, 21 seconds? A little less than that, actually. It's sped up. So this can be useful if you're moving stuff around. You stick a PV in before you start, and then you get a counting on that data rate that's going through. And so if you're saying, oh, I'm going at this rate, and I've moved this much data so far, and I know I have that much data left, divided by that rate, that's how long I have left to go. If you want to see a really big PV number, let's go with PV dev 0 and send it to dev null and give you a sense of just what that looks like. So moving 11 gigabytes per second from memory from dev 0 and sending it to the trash. Just fun. I really use this in production. I've worked on cryptographic equipment, and how quickly can we generate random numbers is a question that's very important for certain operations. So I have cat dev random. Actually, I won't even do that. I'll do pv dev random, and I will send that to dev null. And that's slow. I'm running out of randomness. The crypto engine has run out. So I probably don't have a hardware accelerator in this system. But if you use urandom, which is sort of, but not quite, random-ish, you'll see that I get a pretty decent throughput. So randomness is important because you're doing a Monte Carlo simulation. Urandom's fine. If you're generating cryptographic keys, the speed of random matters.
Have you played with Havage?
Cabbage?
Havaged. I mean,
yeah.
You're vegetarian. I imagine you played with cabbage at
Yes,
some point.
and kale too. But no,
yeah.
I have played with it. There's a lot of controversy around their system.
I mean, there's also a lot of discussion about whether urandom is safe or not. There's a lot of core devs who say that urandom should be fine.
Yeah, and it probably is fine, but it's not provably fine in the same way that true randomness is. And even true randomness has been whitened, so there's a lot of complexity in this ecosystem. But interesting stuff. So problem I actually did solve. How long is it going to take me to generate 100,000 of these things? Answer, measure how quickly I can get entropy. Oop, not fast enough. Okay, install the drivers to enable the entropy gathering from the processor. So that's looking at storage. So now the next thing is I want to look at RAM and swap. So let's go ahead and reset things. Okay, so let's generate some stress. Let's generate some memory stress. So stress ng. Yes, it can generate lots of different kinds of memory stress. I'm going to run one memory hog. I'm going to run VM bytes 70%, so it's going to nominally use 70% of the system's memory, but it doesn't actually usually do that. Don't ask, it's more like 50%. And I'm going to tell it VM hang. So what this says is hang on to that memory. Just allocate it and sit on it. Okay, so I've generated some memory stress. So let's go back to top. So we have these lines in top that show us the memory that's being used. So we can see how much memory we have, how much is free, it's not being used for anything, how much is being used for something, and how much is being used for buffers and cache, and then how much is available. And what do these all mean? Total, that's like how many bytes you got. That's the size of the swimming pool. The free part is the parts of the pool that aren't being used. The used is the parts of the pool which have butts in them. That's being used. And then this buffer and cache is tricky. So these are things the operating system keeps around in case you ask for them twice. And so the idea is if you read a file from a disk, the operating system will read the file into memory and then give you access to that file. And it'll leave it in memory until it has some reason to get rid of it. And the reason why is because you might ask for that file twice. And it doesn't want to have to go back to the disk. And hey, you're not using that RAM for anything, right? You mind if I borrow it? So what that means is that this number largely can be added to the free number. Not completely. It's fiendishly complicated, and I don't even know the answer here. But I just usually say buffers and cache plus free is how much I have. Available is done the fiendishly complicated calculations, and that's how much you have. And you'll notice that this is about 10 times bigger than that. So I may be running low on free memory, but a lot of my memory is available. So if a request came out asking for 750 megs of RAM, the system would say, hold on, go, 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 go. Okay, here, you can have it. It would throw all that cache out, say, no, now I've got a better use for this memory. But if you're dealing with a busy server, if you've got a situation where you don't have much free RAM, you don't have much free memory, and you don't have much buffer and cache, your disk performance is going to collapse because you're not going to be able to optimize that disk as much. So you want to keep an eye out for that. Just because you haven't maximized your memory, if your buffer and cache starts dropping in response to workloads, that's probably a sign that that disk activity is going to become less efficient over time. And so your whole system will slow down.
In these stress, when it asks for a bunch of memory like that, is it do one huge buffer or a bunch of little buffers?
There's paging involved.
Okay.
Give me a second, and I will talk about paging in a second. Page is a good friend of mine. Okay, so the last column we have here is swap. Now swap, who here knows what swap is? Quick show of hands. Okay, so not everybody knows what swap is. So I'm going to explain what swap is really quickly. So your computer has memory. And for various accounting reasons, it keeps track of memory in distinct units. It calls them pages. So it has a page table, and that table consists of little chunks, maybe 4 kilobyte chunks of memory. And so it takes this huge space, breaks it up into a bunch of little chunks, and keeps track of where those chunks are. Okay, that makes sense. At some point, somebody ran into the situation they wanted to run more programs, and they had little chunks, little pages that they could service that program with. That program needed more memory, or there were more programs, and their combined memory usage was bigger. And what they realized was that not all programs are using all parts of their memory at once. If you played a video game, you're not playing the big boss at the end of the level yet. So you don't actually need that in memory. I mean, you might have loaded it because you want it to be there when you get there, but you don't actually need it. Like, you wouldn't notice if it were missing, would you? And so that's what virtual memory is about. Virtual memory says, we're going to keep an eye on RAM, and if we're running low on space, we'll take chunks of memory that don't look like they're being used currently, and we will swap them to the disks. And we will essentially put an IOU in the program. And so when the program tries to use that chunk of memory, the operating system will get something called a page interrupt. It'll stop the program, say, quick, 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 get the monster before it notices. You'll load it back into memory and then start it back up. Okay, so why is this interesting? Swap is going to disk rather than RAM. And this is slowly changing. So I'm going to say something, and don't correct me on this. Disks are a lot slower than memory at the moment. And what that means, and when I say a lot slower, I'm talking tens of thousands, hundreds of thousands of times slower. They're much slower. So it may not seem like a page fault is a big deal, but if you're getting a lot of them, you're going to notice. And so that's why I like VMstat. Because with VMstat, I can see this column here. Swap in, swap out. Am I moving pages in and out of memory? So here it says, okay, you're using a lot of memory, you don't have a lot free, but you're not hitting the swap that hard. Don't worry, you're cool. You're cool. But if I go ahead and change the equation a little bit to, actually I'm going to do 4 of these. So now I'm going to use a heck of a lot of memory. And what you should see, oh, crud, not working the way I want it to. The operating system's a little good at optimizing memory usage. So sometimes it's hard to get swap to be used. Okay, so now there's some swap outs. And that might be the best I can do. Let's see, VM hang. Let's get rid of VM hang. And I get the more swapping going. There we go. Now we've got some good swapping going on. So, why is this useful? Well, first off, you can see my I/O wait has gone up. That means a third of the time I'm just waiting for the disk. And why am I waiting for the disk? Because I'm swapping memory in and out. And that's way slower than using memory that's just directly on a chip. And so this is helpful. This gives you some information. So if I go ahead and use another utility I commonly use called free, this will kind of also give me a good snapshot. So you see I'm out of available RAM, out of buffer and cache. I don't have very much free. And then I see I'm hitting swap a little bit. And so this shows me my system is probably getting slowed down because it doesn't have enough memory. That's what's slowing me down here. So let's make a small change to this. Let's go back to that old memory stressor. And we're going to look at free again. So now this is a completely different analysis, you see. I've got some free memory. I've got some available. The buffers are still a little low. But this is a more healthy system. It's highly utilized, but not tremendously. It's still got about a third free. But if you look at the swap, you'll see that I'm still using a little bit of swap. If this number is small, like less than 100, less than 20 or 30 even, might be a more reasonable value. Don't worry. So you remember how I said the operating system will move things into RAM if it doesn't look like you're using them? Well, it'll page stuff onto disks rather, if it doesn't look like you're using it. Well, another thing it'll do is it'll say, hey, you're using the hard drive to do useful work. And meanwhile, the monster at the end of this level isn't actually doing anything useful right now. So the operating system will actually occasionally page little chunks of memory out to disk to make the disk caches bigger, to speed things up, to put the memory where it'll be useful. So just be aware, this number will always be small. But if you have a small amount of swap usage, it's not a problem. It's the operating system kind of just turning the screws and really cranking that performance a little bit. It's being helpful. I've dealt with a lot of people who have been in monitoring and say, oh, you're using swap. It's terrible. We need to add more memory. And it's like, no. You add more RAM, you'll still end up using a little bit of swap. It's not a big deal. Or they'll say, oh, you're out of free memory. Oh, it's terrible. I said, no, don't worry. The buffers and caches will get freed. We still have plenty of capacity.
I think that's a Windows artifact. Windows tends to melt when you run out of RAM.
Okay, so I've looked at RAM and swap. So I'm going to try to get through networking pretty quickly. So that's the last thing I want to look at. So let's go ahead and set up a stressor. Let's see. Do I have an NC? Yep, cool. So let's cancel the, so is it NC? Yeah. NC listen on port 1234, type it to PV, and send it to dev null. So what I'm doing here is I am running a really crappy server. I'm running it through Peavy, so I can see the data moving into it, and I'm just throwing the data that it receives out. And so now on the Mac side, because I'm simulating kind of two machines talking to each other, I'm going to go ahead and I've got a large file, or I've got dev0, and I am pumping it in with -L 1 megabyte. So what is this? PV-L 1M. So you remember how I said pipe view kind of gives you a sense for how much data is moving back and forth on connections between commands? Well, you can also add rate limits. So say you know your network can handle 10 megabytes per second, and you don't want your roommates getting mad at you. You can go ahead and add a -L and a rate limit to make sure you're not using more than your share of bandwidth. So it'll use that much, but no more, no less. So this is really good for like a congested network, or if you're going over the WAN, the company WAN, you don't want to like knock everybody else's traffic out. I'm a bit of a jerk nowadays. I don't do that, but I used to have to do this a lot because I had a slow WAN. So I'm going ahead and reading essentially at 1 megabyte a second and sending it over the pipe to Netcat, which if we go to the other side here, we'll see now we're receiving data at 1 megabyte a second. So I've simulated something streaming data to a server. So that's our scenario here. So let's learn a little bit from this. So there are a heck of a lot of tools to analyze this type of problem. So I'm going to run through them pretty quickly. So the first thing is our network busy? Like, am I doing something on the network? I know it sounds crazy, but if you don't have network connections to something, it's not the problem. So you should always say, like, my web browser is slow. Well, let's see if your web browser is actually connected to anything. So NetStat can be helpful for that. It'll show you, I'll do numeric and TCP connections. Okay, so I've got SSH running, and I've got this 1, 2, 3, 4. But if I were troubleshooting a web server problem, it means I've got no traffic. That's all. So just make sure you've got something happening before you start. And then the next thing, you can use netstat-i. And what netstat-i does is it gives you some statistics about your interfaces. So you're sending data over a network. You've got a client and a server, and they're moving data back and forth. But is that data moving smoothly? Maybe you've got a bad cable, or you've got an overloaded network switch or router or something like that. Well, this will help give you an idea. So this shows you all of your network interfaces, and it shows you how many packets were received A-OK, how many packets were transmitted A-OK. But then it also shows you errors with packets, dropped packets. Those are packets that were disappeared. They were gotten rid of for some reason. Maybe a buffer ran out of space, so it removed a packet. Or overruns. And so the point is these numbers should be small. If you're looking at it, you shouldn't see these numbers change. If these numbers are anything but very, very small, and I mean, if you're on a server that's been up for like 3 years, yeah, I mean, you'll have like 500, bad packets or something like that. But like, if your server's been on for an hour and you've got some numbers here, you got a problem. You've got a bad cable, a bad network card, some sort of reason that the data is actually not moving smoothly. Who here has done ping to test a network connection? Like, if you have a 1% or a 2% dropped packets, you've got a big problem. Like, that's disproportionate. That really causes a huge performance issue. And this is that kind of analysis, but at a lower level. So look at these. So that's the network statistics. There's also another way of getting this. If you use ifconfig, it'll show you each interface and their network statistics in a slightly different way with slightly nicer numbers, actually. Right? It shows you the units there. So this is just, look for it. Make sure you don't have hardware problems. If you want to understand kind of what is a reasonable expectation for my network? Like, I'm getting data, but is it fast? Well, if you have a fast network interface, 1 megabit per second isn't fast. If you're getting 70 megabits or 500 megabits per second on a gigabit interface, yeah, you're doing a lot of work. That's pretty good. I'd say you probably don't expect much more than that. About 50%, you're probably going to start running into performance problems after that. So how do you find out how fast your network interface is? So there is a program called ETH-Tool. And let's see, ETH-Tool, ETH0. No, that's not the interface names here. There it is. So let's just look at this. So this is super geeky. This is way lower in the stack, but you're looking for something really simple, which is what speed is your interface running at? And here it says the speed is 100 megabits. Okay, cool. If I've got a gigabit card and I'm running at 1,000 megabits. If I get it, so that means I'm running essentially at a gigabit. That's good. But if you've got a gigabit card and you see something like 10 base T half, then you have a problem. And this is in the realm of networking problems. This is lower, just like the same thing I said before. We see errors, look for your cables, look for overloaded networking equipment. It's kind of more physical, most likely, than software.
What are you plugged into on the other end?
Yeah, and how you're getting there.
Yeah.
In this case, what computers will do is when they talk to each other over a network, when they light up a network cable initially, they kind of have to figure out, they're doing sort of a square dance of like, so how fast do you go? How fast do you go? And they try to kind of match each other up and find the fastest common speed that they both support and do that. But this protocol, not everybody implements this as well as they could, and there's differences of opinions on what to say and when to say it. It's a lot like dating, and sometimes you just get the wrong message. And as a result, you take it way too slow. Okay, so that sounds a little jerky. But the point is these two ends of the connection are negotiating a speed, and sometimes they make a bad choice. And so you can look at this and say, what decision was made? Oh, hey, that's a lot slower than I expected it to be. I need to go in and do something about that. Maybe replace the cable, maybe check for compatibility software updates. Maybe I just need to manually set the negotiation speed, which I won't tell you how to do. But this just tells you, like, it's the width of your pipe, stupid. It's not how fast your computer is. You just literally can't get the bytes because your pipe is going too slow. And so that can be very helpful. Another thing I've used, and I will not talk about this in detail, but sometimes you are working on a system where you don't have good tools. And so procnet dev is kind of the raw data that's being processed. I have written utilities that go here and scrape data from it. So if you're on that little router that you've got in your house and you're trying to figure out like what's going on with the network interface, how much data is moving back and forth, and I'm living in BusyBox, so I don't have any good stuff, go here. You can output these numbers. They look better if you have a wider screen, but it'll show you how many packets you're moving, how many you've dropped, and so forth and so on.
Still mostly looks like it's snowing or something.
Yeah, but if you go ahead and say set up a loop and print this every second, then you can see like how much data you're moving per second. So you can kind of write your own IOtop, IOtop, or NetTop, sorry. Okay, so I've looked at IF config tool procnet dev. So there's IFstat. This is really nice. I like this. How much each interface, what interfaces do you have, and how much data is moving in and out of them per second. That's pretty sweet. My network connection busy, and so it's just kind of easy to use, simple. Let's see, IOtop. So if I do IOtop, and I'm going to give it an interface. Let's see what the interface names are. So this is like top for your network. It's not exactly like top. It's similar, but not exactly. But it gives you kind of a really nice view. And the thing you're looking at here is, here I'm going to just switch it to numeric mode and print the ports, just so it's nicer, is who's talking to who and how much data are they moving? You know, is it my network backup to backup.internal, or is it my chat traffic because I'm downloading a large cat video from my coworker from Slack. You can look at it and it's like, oh, the Slack traffic is actually swamping the connection. It's the thing that's the big one. It's the network backups running nice and slow. So this kind of gives you a sense of the flows and how fast they're moving. I'm not going to get into this too much, but I will say the units here are a little wonky. These are 2-second units, 10 seconds units, and 40 seconds. So an average over 2 seconds, a per second average over 2, a per second average over 10, a per second average over 40 seconds, over the last 40 seconds. It's just kind of weird. The other thing is those units are in megabits, not bytes. So if you really want to understand something in a human type unit, use it like this. And this will look a lot more familiar. That is a megabyte. That resembles something I'm used to dealing with. Megabits, not so used to it. So that's just adding a capital B option to the command. Then there's another one called nethogs. This is pretty awesome. I like nethogs. I haven't used it much in production, but it's essentially top for your network activity. So it says, hey, here is the busiest program. So like, what program is sucking down my network bandwidth? This will answer that. So previously we were looking at how busy the system was. We're looking at how busy the interfaces were. We're looking at how busy certain connections were. But what's doing the work? This lets us know how busy program. Very handy for that, super easy to use. And the last thing is, and I'm going to just briefly show this, is IP trap. And the reason why I'm using this is that it is just really easy to use. Okay, so I've got to make the screen bigger. Pardon me.
Command minus a couple of times?
Yeah.
That just changes the font size of it. Yeah.
There we go. And so the nice thing is it's kind of got a little bit of a GUI. So you can kind of look at like, okay, here's what's going on in this interface, and here are the traffic flows, and you can say more detail on that. And I'm not going to really get into it because it's pretty easy to use. But it just kind of gives you a sense, a really nice representation of lots of the statistics, and they're easy to use, and you can do filtering and so forth.
So I guess give a bit of context to why I asked for a visualization for network. When I have my MacBook here, or even my iMac at home, I have a firewall called Little Snitch, and it gives you this nice little traffic map of all of your current and past connections, and all of a sudden you see packets flying to Russia, and you're like, why am I talking to Russia? I don't need to do that right now. I'm surfing maybe like, Google Drive or something, and that's it. Being able to just glance at something and be like, why is there this huge visual assault from a foreign country?
But that isn't the bottleneck.
Right. that was just what I was asking.
But it is an interesting and definitely a worthwhile use. And so, I have been focusing on like why it's slow. What's slowing down my program? What do I need to buy or speed up?
Denial of service attacks are bottlenecks.
Yeah. But am I under a denial of service attack, or am I just downloading lots of cat videos?
Right.
Is there a difference?
Right.
Back to the swap stuff, back in the day, like before Y2K, I found it easy to do, advantageous to set up another physical drive as a swap space.
Yeah. And that's because you wouldn't have to deal with disk contention on that swap disk. So if you start swapping heavily, at least you wouldn't get in line behind the download of cat videos. Because that's what you were doing before Y2K. but no, and that's a sensible strategy, absolutely. But frankly, if you're using swap space actively, like if you jump and take a huge chunk of swap space and just sit on it for a while, it's actually probably not a problem. But that swap in, swap out, That's
Yeah.
the problem. It's moving it back and forth, and that's why VMstat's so nice. It doesn't show you what you're using. It shows you how active it is, how much is moving in and out, and that's the thing that'll kill you. So I'm way over my time. Any more questions? Well, thank you. Hopefully you guys got some cool utilities. Like I said, this was meant to be fast, quick, and dirty.
Fast, quick, and dirty, picture.
Oh, sorry.